Okay, sure. Uh, anyways, so so today's thing, today's today we'll just start off with differential geometry. Looking into so the idea here is not to go in detail into the calculations. Like we'll keep a separate session for the calculations themselves. But the idea is first to familiarize yourself with the objects of differential geometry. Most of the time, um, the we forget what we are dealing with when it comes to say vectors or like tangent spaces or even simple things such as bases, right? So we just sometimes often like just completely forget what it is exactly that we are dealing with, and most of the time it's a hard time coming back, reading back from whatever we're learning, and then rethinking about certain basic things in a different light, right? So that's a process that keeps happening. But through this process, it is important to have that initial clarity of what exactly you're trying to do here. Why exactly are you setting up this whole formalism? And secondly, like beyond the intuitive understanding, there is also a necessity for the familiarization with some of the formalism. So, because what happens is different. So, as the saying goes, every differential geometry textbook has a different formalism, and most of the time, like especially in my own working, like uh, three or four different textbooks, everything has completely different formalism. No, there is no. And every differential geometry book, whether it be advanced differential geometry for like physicists, like gauge fields and geometry or something like that, gauge fields and knots by Bayes, or whether it be Kobayashi no Mizu, which is a more mathematical perspective, or whether it be pure mathematics. Every book has like its own set of formalism, and it's kind of like the introduction takes up half or like quarter of the first book. So just getting into the formalisms, into the whole thing, it becomes a big deal, and then most often you never really get to the beauty of. Uh, it takes a really long time and a lot of persistence to get to the beauty of what is waiting for you. So the idea here is to probably help simplify these notions, and as you work along, maybe try to put different kinds of perspectives in like different viewpoints in perspective. So try to introduce some sort of like a variable formalism, where we don't really focus on the formalism, except we do focus on the formalism, but rather we just focus on the idea. It's like kind of a dual approach that I'm trying to take here. So that will be the goal for the next few session. With that in mind, let's just start off with the very basic, like of course, like you know what a manifold is, and what a manifold is like. So you have some sort of a mapping, and then you have an atlas to you have a map, and then you have an atlas to denote the coordinates on the map in a very broad sense. So that can be put in terms of like having a function or having like some sort of a curve space, and it's often you come across some sort of a curve space that is called as your manifold, and then you have like a trajectory on your manifold, and that's called as the atlas or the chart, like in the manifold, right? So let's break things down, okay? So first of all, the idea of manifolds comes into the picture when you have multivariable calculus. Obviously, when you have multivariable calculus, two things become very dominant, right? The first one, it does not matter what names we are using to describe the variables. Secondly, like it is possible to give different name to different to talk about different things, to talk about the same thing in different manners rather. So for example, if I'm trying to it's like synonyms. Every object that we're dealing with has several different synonyms, and then you can try to approach the object from several different viewpoints. And the idea to the most important thing to do that is you need to get rid of the attachment of the meaning of the whole concept to the word that it denotes. So for example, when you say sun, okay, so you need not be looking exactly, like you need to be able to visualize the entirety of the sun, and not just the kind of like either the sun in the solar system, or like something like that, like sun as a star, or the rays of sun that give rise to photosynthesis, or like these are like individual perspectives of the word sun. But the core idea is rather abstract. So differential geometry, in fact, becomes extremely exciting, primarily because you're dealing with the abstract, and you recognize that the abstract doesn't really have to attach to a certain name. So, but at the same time, you can look at the abstract from several different variables. Can deal with abstract using several names. So for example, like a few just general mathematical examples. One, you can rename, so if you have a coordinate basis, okay, for like say a function at this matter, at this point, let's just have a general function, and let's have a coordinate basis for that function. So this is x and this is y, and this is some f of x and y, right? Obviously you can rotate this basis without any major difference, right? You can say there is a new x dash and y dash, or you can say you can interchange the switch the bases. You can do all sorts of this thing, combinations. In fact, one thing that I just want to mention out here is that this, like, or you can even like displace the basis to some other point, right? So you can displace the origin and shift the function to some other point, or like you can basically change the names of the variables that you are trying to describe the function with. So one of the an interesting story here is Google Maps, right? So I was watching this documentary on like the suppose like these people patented on Google Maps before like on the algorithm used for Google Maps, and basically Google copyrighted that, like violated the copyright claim, and that's the whole story. But the idea is, so you while using Google Maps, so the initial structure of Google Maps was like, okay, you have a globe, and the globe has several patches. Like, so for example, as you slowly rotate, you have like chart paper. So it's like essentially like when you see a globe, you see a 2D projection of the globe, right? So each 2D projection of the globe is captured, and it is like assigned some sort of a continuity. And then when you zoom in into the globe, onto a particular country or something like that, there are several satellite images which are patched up together. So as you zoom, so it's like so you have the globe, which is like some 3 or 4 different images, and then each image is further broken down into 2, or like some say 4 smaller images. So when you zoom in, you actually end up locating one of these smaller images. Okay, so and then you go further and further and further and further down until you say you find some like the city you're looking for. Okay, so you find the city that you're looking for. Now the problem with the problem with this was, if you try to zoom further, or if you try to like reach an arbitrary close distance to the zoom, the image would get, like, it would start quaking. So that was because your idea of continuity was really difficult to establish in this. So as you broke down into several different like pixels, like several different sub pictures or sub maps, your establishment of continuity at some point started breaking down. So that yeah, so essentially these people wanted a smooth interface. So when you zoomed in, so for example, if I zoom in on this, so I want to zoom in onto this this particular this thing app itself. I want, like, in this particular image itself, I'm zooming in further. But then when I zoom in on here, like, I want this to break down into several images, and then each image starts referencing a particular sub image. Okay, so that, like, there is a discrete nature of like the images, but at the same time there's a this thing, there's some sort of a there's some sort of what do you say, like uh, a jar or a stutter. So when you go from like a bigger picture to the smaller picture, this was overcome, but when it came arbitrarily close, it started quaking. So there was some problem with the algorithm essentially, and the idea was, instead of having a particular so it was like it's and to make things even more complicated, each image was given a search index. So it would take down to that search index, and then it would zoom. So it would take you to the search index and then zoom. Take you to the search index and then zoom. So basically, you had a name for each of the image, and then you could go to that. But beyond like a particular point, the search results themselves started like kind of, for example, if it is two arbitrarily closed places, okay, and then you have two different maps, you don't know which map to go to, so you'll kind of start quaking. So basically what these people decided to do was they just decided to uh, impose a free float coordinate system. So this basic algorithm of free float involved from just going down, from the total, like the big picture, to wherever you want without having any name, right? So in the sense, they actually ended up building a globe instead of kind of algorithmic picture of like subsets of the globe. So yeah, but it's also the zoom and the depth. So if the satellite is, yeah, so okay, so if you look at the computer programming point of view, so how do you so all they had to start with was like a collection of maps, a bunch of maps. Okay, and maps are what? Basically satellite images. So you have a big satellite image of the globe, and then you have satellite image of a country, of several countries, and then of cities, and like, so they had to collect like several independent satellite maps and then put them together. So instead of that, what they did was like they stitched the maps together to form a globe. So instead of referencing by picture, They stitched the map together to form a globe and imposed a free-falling coordinate system. Okay, so instead of like a binary or like a mechanical, like some sort of a loop for looking zooming in into a particular location, they had like a globe and they zoomed in onto the globe. So that was the difference. Anyways, the idea behind the story is, so when you try to describe a function and you really like find it much more suitable to talk about the function itself rather than restrict it to the variables that are involved, because the variables, so if you just put a particular like coordinate axis or coordinate basis, so oftentimes your coordinate basis is not sufficient, and oftentimes it becomes very difficult to compute the change of the coordinate basis and all of that. So we need a simpler algorithm, or we need a simple, like, I mean, no, not an algorithm, we need a simpler picture of looking at a function and its coordinates. So if you draw a picture like this, like, right, for example, the first picture that I drew, right, with just x and y and there is a function, you are restricted to the function thinking that the function is dependent only on x and y, whereas it can be in fact dependent on any two variables. And you can look at the functions from several different points of view based on how you define your x and y. So that defining of x and y itself, it requires some construction. That is what we're trying to get to. So when I say like a coordinate free system, so it means that I am taking into consideration how exactly is it that I'm defining x and y. I'm taking into consideration all the manipulations that I'm doing, so that when I change x and y to something, x dash and y dash, I can easily keep track of how everything changes. So that is the idea behind whenever you, and like even in GR, you often encounter terms like there is no, there is no defined coordinate basis, or there is no so you don't have like a particular a particular reference frame. Okay, you don't have a fixed reference frame, you have to fix the reference frame. You don't have like like it's like you can put an observer anywhere on the function, and based on where the observer is standing, you can define the coordinate basis. So basically that becomes the idea behind this free floating coordinate system, right? So when so to define so moving beyond that, right, just keeping that in mind, that whenever you encounter whatever you encounter in differential geometry is coordinate free. The bases are coordinate free. That means it is you can arbitrarily choose your coordinates as the system sees fit. Okay, and this kind of manipulation has some interesting algebraic properties which we will see soon. Okay, but moving on from that, we'll like talk about what a curve is, and today we'll like talk about what a curve is, and we'll explore what tangent bases are. Okay, so so first of all, talking about a curve is defined as gamma, which is a mapping of R, that is the of a real number parameterized by T to a manifold M. And of course, when I say a manifold, so that means that you are taking each point T belonging to R and transforming it to a point on M defined by gamma of T belonging to M. Okay, so you are taking each point on T and mapping it to gamma of T. Now again, keep in mind that the way T is parameterizing gamma here is different from the way we will talk about T soon. Okay, so this is just to say that, okay, given given a particular curve, you can say that the curve belongs to a particular point. So for example, if you have f of x right? So this is f of x. This is one dimensional manifold. So if you have f of x and x, so then you have this gamma of okay, so this is, by the way, this is gamma of x, right? So now your f of x is the real axis, so it's a real number, and you can say that this belongs to t, so it's parameterized by t here, and instead of, so basically substitute t for x in this, so f of t, and then t, and then you have gamma of t, and then yeah, so now you get the whole picture, right? Hmm. Exactly. So the manifold is x here, I mean, or the t, the x-axis. So this is given by the manifold. So you can rename t to t prime, to t double prime, or triple prime, or whatever it is. So you can just change the whole set of coordinates. You can change the parameter that you're talking about. And then you have, the idea is this curve gamma of t does not change. The value, the mapping, the way it is mapped to f of t will change. The way t itself is defined can change, but the mapping, the kind of like the gamma t or the abstract curve that we draw here, the shape of the curve, so we can say it does not change. So I mean, does that clear up the question? Okay, okay. Okay, so now gamma t belongs to M and t belongs to R. So and then typically, generally, we have uh, since we are dealing with an n-dimensional space. So for example, this can be x, y, and then g is on. So that can be an n-dimensional space, and then you have f of x, y, z, t, whatever it is. So therefore, we have a broader definition for gamma would be I, a mapping from I, that is the identity matrix, to M. And why the identity matrix? Because it gives a kind of a linear space. So it gives an n tuple. So n variables, n dimensional space, which are all independent of each other, like linearly independent of each other, and then that gets mapped to M. So instead of just one variable, you have multiple variables. That's all essentially. And then you can also see the algebraic manipulation if you're interested. So then you have the coordinate presentation of gamma. So this is also a tricky point, right? So your coordinate, okay, or coordinate free presentation of gamma. Okay, so gamma cap is given by phi dot gamma, which is nothing but the mapping of r of t to and r n of x1 comma xn, where your phi is defined by some arbitrary mapping of like the gamma to a n vector basis, like n basis, an n dimensional space with a coordinate, like with a set of variables to describe the coordinate. So basically, this is like, it's like a more mathematical, mathematically, rigorous way of saying that phi gives you the coordinate chart, or the kind of coordinate basis that we are using to talk about the gamma. So without the gamma, uh, without the phi, the gamma doesn't make any. So this is not coordinate free, but rather this is the coordinate presentation. So gamma cap gives you the actual value, like the shape of the gamma curve in t in according to the basis, So without the phi, it makes no sense. So gamma will just be a number. There is no connection gamma of t. Hmm? This one. Yeah, it's mapping from theta to r of n, where n has the n dimensions are specified, are labeled. Hmm? Theta is some arbitrary thing. So it's like you're talking about gamma, you haven't defined gamma at all. So you're just like given an arbitrary gamma is some sort of a mapping. That's all it is. But you haven't like gone back to the roots of gamma. So like similarly, theta is something abstract, and when you like put so phi is basically an operator now. So when you put phi with gamma, then it makes sense. So then it gives you the coordinates of gamma. Like it enables you to talk about, instead of just gamma of t which returns you one value, you can talk about gamma of t in a basis, in a coordinate basis. So that is essentially what phi does. So gamma cap is typically you're putting it into a basis. So that means, yeah. So exactly. So what we're doing here is we are changing our parameter from t to so in the curve we are giving it a local basis. So this is x1 of t, and then so on xn of t. So on the curve we are giving it a local basis, right? So and this basis can be shifted to something that is global as well, by saying this is x1 of gamma of t with x1 n of gamma of t. Okay, so you're shifting from one variable to essentially you're giving a basis. And then if you're giving a global basis, then it is x1 of gamma of t. Right. So that's essentially what it is. And then now if you have, I'm not used to the eraser function on my pencil. So it's like, so global basis is, okay. So yeah, a global is like your, like it's on a point. Or like local is like typically located to a point or a neighborhood of that point, whereas global is if you are using, for example, if you have a curved, if you have like a curved surface, right? Like for example, if you have some object, some complicated object like this with some curve, right? You can't impose a real like Cartesian like or a Euclidean coordinate chart anywhere, right? So you can't, but when you take this whole thing and then you put the whole thing in a bigger like coordinate patch, that is global. So if you say, so what your Newtonian mechanics usually uses a global coordinate system. So like it's like you have this in a bigger in the room. So the corners of the room will serve as the coordinate axis. But when you talk about locally, so your coordinate patch, so if you take a small square, okay, and so this square, the L here, it gives you the let's say the basis, right? So at each point, as you slide along, the basis kind of changes, and then you need a way to connect these bases. That is what T gives you, by the way. So T gives you the parameterization of the basis as well, which we will see soon. But that is the local thing. At T, it is local. Like when you talk about the function itself, the curve itself, it is global. So I mean, like when you put up, so it's basically bigger coordinate axis and coordinate basis, and smaller coordinate basis. If you want a simpler sense of the definition. Then you have essentially, and now after talking about what curves are, we can define. Okay, by the way, these are not functions yet. So functions have yet to be defined. So this is a general curve. And now a function is given by a mapping of M to R. So that is, you have a curve and you have some sort of a coordinate description of the curve associated with it, but that is independent. So that is another mapping. So note that right, when you have I to M, you're mapping I or R of T to M, and then you're mapping M to R. So that's what a function is. So basically a function is you have a curve and then you're mapping it to something else. You're mapping it, so you're mapping each point on the curve to some other point, to a real number. Okay, by the way, I think I did make a mistake here in the sense, in this diagram, in the sense that this should not be f of t, because we are just talking about gamma of t. So these are like, so I just gave an example of how we were talking about r, like the mapping to r of t, or a parameterization, but in fact the parameterization is local. So that means that this is T naught and then this is T. So you don't really have like the R, like independent axis, and that serves as the parameterization. No, it can serve, but it's not necessary. So when I just have this as another coordinate, so this is xi and this is x, say x1 and then x2, okay. So then you have a coordinate basis. Then this mapping, so basically you don't have a function yet. You have a curved surface, or you have just a general curve on a surface. And then when you're mapping that curve to when you're mapping from that place, from the curve to a real number, that is when your function gets established. So for example, if you have x and y, your f of x and y is in this z-axis, and that like gives you a plane, right? So that is what a function does. So it just lifts, it's like kind of a lift. Okay. So this means, so f is given by, instead of talking about x, you have f of x belonging to R. So you have each coordinate, and each coordinate is associated a number. Okay, so this is what a function is. Of course, like you have the definitions of smoothness and continuity and all of that when you're talking about actual functions, and most of the time we will be dealing with analytical functions. So leaving all the trivia aside, let's just move on to understand. So similarly, like how we define the curve, we can give a coordinate presentation of the function itself, which is given by f of f cap, which is nothing but f inverse. That is a mapping from Rn to R. Okay, so it's like, so this function is a function without a coordinate this thing per se. Like it's like so it's like you don't have the specific coordinates of a function, but you're just generally talking about the function. But then when you shift to a particular point on the whole thing, on the manifold, then you can give a coordinate presentation to the function. So most of the times f cap means something that is local. So for example, if it is I don't know how to, again, these are all very like abstract things that you need to think about, because what is a coordinate free description of a thing, right? Of course you can draw a curve somewhere and say that this is a coordinate free description of the thing, but like what does the curve mean? The thing is, it has no meaning unless you give it all these descriptions and all these definitions. So yeah, so how the whole idea is to recognize that there is something that has no meaning, and recognize how we are giving it the sense of meaning by adding all these coordinate presentations and giving tangent spaces and all of that. Okay, so once you have understood it, we'll just move on quickly to the tangent, the notion of the tangent space. So with the tangent space, there are like four broad definitions that I want to, like four definitions of a tangent space, what it means to talk about a tangent space, that I'll touch upon. And three of them, like two of them will be very quick, and two of them I'll go into a little bit of detail, right? So now we have a random curve. Let's not talk about any basis, coordinate basis or anything. We just have a random arbitrary curve. Okay, and then we have I just want to make it intersect. So yeah, so these two curves are intersecting at just one point. So this curve is gamma 1 of t. Again, note that I'm parameterizing these two curves by the same variable. That is why I can just kind of like say that they are intersecting at like the same point, right? This is some sort of like this level of abstraction is something that you need to understand for your definition of like your Lie derivatives or Lie algebra. So just note that I'm just trying to fix a uniform parameterization for all my curves. So how do I do that? Again, it is based on assumption that they are in the same space and they have like there is a possibility that they can intersect, and the two variables are essentially indeed connected, right? So the parametric variables are connected. So so the first definition of this of a tangent space is given by curves, essentially curves tangent to a point. So you have a collection of all the curves that are tangential to a point, that intersect at a point and nowhere else, or like locally at least. So this gives you a description of the tangent space of a point. Okay, so it's kind of like you have infinitely many curves again. So let's just look at this, and then let's just define it a little more, using getting the insight into the formalism that are involved. So we have gamma 1 of 0. So we say p is at t is equal to 0 is equal to gamma 2 of 0 is equal to p. So p is at t is equal to 0. Now the idea is that the curves intersect at this particular point, right? So we have the derivative d by dt at 0 of xi, that is the coordinate projection of your gamma 1 of t, is equal to d by dt at t is equal to 0 of your xi of gamma 2 of t. Right, so this is basically saying that these two curves intersect, parameterized by t. Now again, how we have defined t is very vague. It's very arbitrary. And this is one of the fun things that we will just touch upon at the end of today. So, so we not okay, not the end of today, the end of today's session. Okay. Anyway, so we have T, the tangent space T P M defined by the set of equivalent classes of of curve, and in this case you have like gamma 1 comma gamma 2. Okay, so this is an equivalent class, and let's define what an equivalent class is. For that we need to do a Taylor expansion around the point. So when we do the Taylor expansion of the coordinates around the point P, okay, so it is just xi, right? The coordinates at point P is xi. Now when we do a Taylor expansion around this point, we see that xi of gamma 1 of T is given by xi of P plus some tai plus O of T. And now you have xi of gamma 2 of T is given by xi of T plus some pi plus order of T. Okay. Yeah, yeah, yeah. Okay. Yes, higher order of like we just represent it as some order of T, some polynomial of T. Okay, so but essentially for these two curves to be equal, so d by dt is equal to 0. That means ai is equal to b. Like then you have like ai and bi can be two independent things, and it doesn't matter when you say the derivatives are equal to 0, right? So essentially, then what? Sorry, my bad. Then AI and BI must be the same. If you want to talk about an equivalent classes, a class of curve, then AI and BI must be the same, because the t can, like when you take the derivative with respect to t, then the t's cancel out. So you have AI equal to BI. So according to the upper definition here. So when you take the Taylor expansion of xi of t, and then again t is some random parameter which we are using here, right? So to get the derivative in place. So right. Exactly. So AI is equal to BI because they are meeting at the tangent. So that means that when you have a tangent point at like tangential curve, you must have a common tangent. Okay, so let's just look at this a little more. So if you have v is equal to d gamma 1 by dt is equal to gamma 1 dot is the collection of the equivalent classes of gamma 1, uh, uh, and then you have w is equal to d gamma 2 by dt, which is gamma 2 dot, which is also written this way. Then so just like if we denote the names v and w to do these two things, two vectors, we find that the v and w have to be equivalent to each other, right? So because at point P, but also we find that like there are certain like tangent vectors that are in like up not at the point P itself as well. So we just have some sort of a notion of tangents for the curve. Okay, and at P, v is equal to w. At P, I mean, yeah, we yes, the definition of has to depend on like smooth, continuous curves. Like you can't have some sort of an like a cut off and then like yeah, you can't have a tangent. You can't define a tangent at a point which is like with at an any point of curve. So, hmm. No, then it will have multiple points of intersection and then it cannot be a tangent. Okay, so if you okay, so if, what you're saying is if you have some sort of curve like this, okay, and then you have something here, right? This is what you're trying to say, right? Then the point here will have a different tangent, common tangent. It will have a different common tangent. It will be like it's just for a different curve at a different point that you're talking about. Okay, it doesn't matter where the point is or how the curves are made, like made. The very definition of tangent curve is in this definition. And then when you take the derivative of with respect to t, then yeah, it has to be equal to dx. Right? So exactly. But also note that the O or order of t square and etc. other terms, we're not talking about that yet, right? And this idea of having a second order to kind of define and concretize everything that we have been talking about, it shows up very beautifully in this theorem. So like yeah, so it's like yeah, we'll get to that point later, but just note that this is the first order of expansion. So you can have a second order and higher orders of expansion, but then we will see how that makes sense. But also note that for all like real and analytic purposes, your first order is like a good enough approximation to give you some basic tool set to play around with. So then, okay, so these vectors v and w, they have notions of linearity and etc. to give to be able to play around. For example, if you have uh, xi of gamma 1 plus lambda, some linear combination of lambda gamma 2 is equal to, again we can have some sort of like a definition for a new curve, like adding these two things, have some linear combination of. So of t is given by xi of t plus t of ai plus lambda bi plus higher orders of t. Right, so this is just one thing that you can keep in mind, and then this gives you this definition, gives you the idea that uh, all the tangents belong to a linear space. So basically we can, so just note tangents belong to linear space. Okay, so now moving on from definition 1 to definition 2. Definition 2 says that these vectors are can be, or tangents can be defined as directional derivatives. So what do I mean when I say that? Imagine f of m is the collection of all the functions f belonging to like that map M to R. Okay, and the smooth functions on M. And now uh, given a vector v belonging to the tangent space of M, we can say that v cap is defined by a mapping f of M to R. So essentially for each f we are giving a number mapping to R. Each function f we are giving a number mapping to R. So that is essentially your f is now changed to v, f become v cap of f, which is defined by d by dt at 0 of f of gamma of t, which is nothing but the directional derivative of f in like t. So obviously you can give it the coordinate presentation of Rn and say that you have like the partial derivative, the sum of partial derivatives, which gives you the actual definition of the directional derivative. But yeah, this is essentially what it means. So then V is defined as gamma dot. So the vector is the directional derivative of gamma. So this also leads to interesting properties, which we will talk about soon. And then we have essentially we can denote. So basically, then we can talk about instead of if we choose to break down t and t to r n of x. So if you have this breakdown, then you can essentially write a basis ei is equal to dou by dou xi, okay, and therefore you have dou by dou xi is given by ei of f. So when you apply, so this is given the tangent space of your function, right? So then instead of like from, so what we have done here, if you note, is instead of talking about random curves and tangent spaces of random curves, we have said that the curves are functions, and we have said that the d by dt is nothing but the directional derivative of the function. We have given this linear decomposition to the whole thing. So given this, so this is also written as at p. Note that this is at p. Okay, so f at p. So you need to describe it locally. So that is given by dou I at p of f. Okay, the partial derivative. This is the dou I is nothing but dou by dou xi, right? And moving on to the third definition. So this whole setup here, if you think about it, it can be a first order. So your tangent space can be a first order differential operator with some ai, which is a constant, and then you have dou I at point p with its particular linear combinations ai dou I at p plus lambda bi dou I at p is given by ai plus lambda bi dou I at p. So that's the linear combination, saying that you can like mix and match the coefficients because they belong to a linear space. Yeah, exactly. So you're just extrapolating the second definition to a certain extent by allowing for some constants to also come into it. into play. You don't need to have the exact directional derivative as this thing, but you can have some sort of again coordinate free, like yeah. So you need to not fix it upon the directional derivative. So you can have some sort of a combination. So then your definition 4 is like the one that you encounter in your normal mathematics textbooks, which is kind of boring, which doesn't give any sense of meaning, or like doesn't talk much unless you do too much of like and then like later on you define things, right? But it doesn't give you this idea and insight in the very at the word go. So that definition is basically you have tangent space is nothing but the mapping of xi to x dash I of x, such that ai is given by jij of p aj. So you have the Jacobian introduced for any change of coordinates, and essentially you just have like your coordinate can change to another coordinate given by a particular Jacobian. That's essentially what it talks about. It maps like it just gives you n real numbers, also I mean n tuple, like n like tuple associated with n real numbers, and then the change between each like tuple, like the change of coordinates and all that is given by your Jacobian. So that is what which one? Xi to x dash y. No, it need not be. It's just any coordinate. So if you have a coordinate basis at like at point P given by xi, and you can change it to x dash y, x dash I of x itself. Because when you see this definition, this collection of objects is the only possible sort of is the only solution to this particular problem. So it's like a collection of like it's the most simple solution rather. You do have, so this is the most abstract definition notion. So for example, so this is like just saying that if there is a curve, okay, then it can be given by a coordinate basis xi, okay, and then you can change it like a coordinate basis at a point xi, then you can change it to x prime I. So you can just change it. So it doesn't like, and note that this entire basis itself that you're defining there at a particular point gives you your notion of a tangent space. It need not be the tangent vector, but it is the tangent space. Similarly, how we see in this definition 3 that it need not be the exact tangent vector, that is the directional derivative, but it can be some for like combination, arbitrary combination. But it's a first order derivative operator, like the first order operator. Yeah, like no, I mean it's not about curving at all at this point. Definition 4 is just about that particular local description of coordinate. It can be changed according to your Jacobian change of like the rule for change of vectors, for transformation of vectors. So it's not really, so it's just you're defining a linear space around a particular point. In other words, a tangent space is just a linear space around a particular point. And you have an arbitrary basis whose rules are given by the this thing, the Leibniz rule, of course, like this is like you do have the Leibniz rule and all of that coming into picture when you talk about this thing, right? So basically, uh, you have your um, neighborhood of a point P, okay, given by tangent space. Not, it's not exactly the neighborhood either. It's just like you're mapping the point P, and then you're extrapolating a linear space from the point P. You're like taking point P, and then you have like that as like that opens up into a linear space. So that is essentially what we're talking about here. So right, again, definitions are like so this is the most abstract definition of them all, and then you end up like in more general mathematics text, you end up going from this definition to refining and refining and refining and refining and arriving at this definition. So that is the general way, but for intuition, this definition 1 to 4 makes a lot more sense. Okay, and today the final thing that I want to touch upon is the notion. Okay, I just want you to think about it. I'm not going to explain it at all. I'm just going to write it down, and then I want you to think about it. Okay, so so an integral curve is given by d gamma by dt is equal to v, which is nothing but dou I of f. So it says that the directional derivative is essentially the same as some sort of a like of a vector field is the same as the variation like the tangent of a curve. So yeah. So this is another definition. This is what a vector field means, and just think about it. Just meditate on this. I won't go into the details because I just want to see like what kind of thoughts this leads to. Just this expression itself, what it leads to. So yeah, just go upon this, and I think that's it for today. So yeah, so tomorrow we'll be continuing with this, and then we'll be bringing, probably we'll be talking about metrics and more of like, yeah, the very Jacobian transformation that we saw there, and then we'll like get acquainted with more ideas of the manifold perhaps. So essentially in review, right? So yeah, so we have your definition of curves and your functions and all of that, and then you have 4 definitions for tangent space, and we see how the tangent space is nothing but some sort of like a linear first order operator defined at a particular point of a function. So essentially, yeah, and then from this very definition, you can in fact jump to the directional derivative being the time derivative of gamma. So what is gamma here? How does gamma and f relate to each other? How do they relate to each other? Is something that you need to figure out. Like it's something that will be fun to figure out as an exercise. So yeah, that's essentially it for today. I stopped the recording.